Yes. Are we going to use pencils? Yes. We're even going to use letters of the alphabet and the Greek alphabet. Yes. So those are all important tools, but they're not the main tool. The main tool is what is the physical picture of what's going on. So, see if this helps if you don't see the 2 meters yet. Pretend, just for the sake of argument, that this can't move. This is bolted to the ground and this is a rubber band. If you were to pull this 1 meter, wouldn't you need to have stretched the rubber band out to here? Wouldn't you need an extra 1 meter on top and 1 meter on bottom? That rubber band is going to need to be 2 meters longer in order to stretch out there. Now the reality of this situation, it is not a rubber band. It is not stretching. And this is not stationary. And so what happens is this whole string does not get any longer. What happens to it? It moves over, giving up its 2 meters right here. And so it is going to move to right here. And so there is how it does. It moves over 2 meters. And like I said, if you don't see that, you're going to run yourself into some difficulties here, because just like in the problem before, if this goes 1 meter down, then this moves 2 meters over. This covers twice the distance of that one. That means if this one is going down with a speed of 2, then this is going over with a speed of 4. Maybe symbols would be more helpful. If I were to call this distance R2 going down, and call this distance R1 going over, right here, well, maybe I'll put it right here. Right here, I could write R1 is 2 times R2, right? However far this one moves, double it for that one. Got a good physical picture of what's going on? There's step 1. And a little harder one, I must admit. Because that's really our first question. Let me read first question A. If A1 and A2 are the accelerations of M1 and M2 respectively, what is the relationship between these two accelerations? How is A1 related? Does A1 equal A2? No. And you might be able to see it. If you see the distance, how do you get from distance to acceleration? Take the derivative twice. So I'll take the derivative 1 time. That's a great question. I don't think so, but let me double check. I hope I'm doing it backwards. So if this goes down 1 meter, this moves over 2 meters. So I want to take this distance, R2. I want to multiply it by 2 to get that distance. Yeah. So if this is a 1, 1 times 2 is a 2. If this is, yeah. Was that your question too, or? Yeah. Okay. Well, now back to this question about velocities. This is our answer to here. Wouldn't this be then velocity of number 1 equals twice the velocity of number 2? Isn't that what that's saying? Did I take the derivative? So again, remember that. You just get a whole 4 sections there, right? I'll put it here on the board here. This is what these first 4 chapters were about. Can you go between position, velocity, and acceleration? Because after we do this, now we're going to say this is the connection between net force, and net force is the sum of the individual forces. So this is our chapters 5 and 6 that we'll be studying here. And then, actually let me incorporate it to here. And then this is our chapters 1 through 4. So 1 through 4, you just did a test. We just went over the test. You've been studying it. And then this is what we went over, of course, before the test as well as this week, is add up all these forces. What is the sum of all the forces? Well, in either case, there's the velocities. Could you get the relationship between acceleration? Did you take the derivative again? So the derivative of the velocity with respect to time is 2 times the derivative of number 2. That derivative there is the acceleration of number 1, and that one is the acceleration of number 2. Okay? So we can answer A. What's the relationship between the accelerations? Well, knowing the acceleration of block 2, you double it, you get the acceleration of block 1. Okay? Did you notice I also picked my coordinate system here? Don't they both have to be positive or both be negative here together? If this goes down and this goes over, haven't I picked those to be the same sign? So just like we did on the problem before, I would encourage you, well, let's call this positive x and call this positive x. But in this case, I've actually begun to make that decision already. And it goes back to what I was saying before. Make sure you're paying attention to what you've done, what decisions you've made, because sometimes you made some subtlety decisions along the way and can get yourself into trouble if you think you can pick which way is positive or now. And if you were to pick this to be negative down and this to be positive over, then this equation wouldn't work. It should have a negative sign with it, and that's not what you have. So this is going to be a useful equation, but only valid if I call the same direction, either both positive or perhaps both negative, but I might as well call them both positive. Does that make sense? Well, I'll keep going, because there's A. What is the relationship to those accelerations? And notice I got it mostly by the physical picture. Yeah, I took a couple little derivatives there, but that wasn't a hard thing. I mean, the derivative of that's not hard. Maybe interpreting what the derivative means may be a little bit harder, but that was the hard one right there. That's a 2-to-1 ratio. Got that from the picture. Then it goes on, and it's very similar to the problem we just did. Go ahead and find the tensions in each of the string and then see what is the acceleration of each of the blocks. So we've got 2 different tensions and 2 different accelerations. Find them. Find those 4 things. All right. So now we're off to this free body diagram stuff again. So I did one free body diagram. I should probably do the other free body diagram. Let me give a little space here so I can work between them. But there's free body diagram number 1. Here's free body diagram number 2. I'll place this up here. What forces are acting on this one? Well, this is like the one we had before. It's M2 pulling down. And in this case, I have this string pulling up, right? Isn't this a different string than this one? So let's call this then T2. And so this is the tension in that string. Not necessarily the same tension in that one, which is again more of the reason why this is a little bit harder problem than the one we did before here. But now that I've done my free body diagram, let's go to step 3. Can you write out all the equations? So let's pick a coordinate system that says to the right is a positive x and up is a y. To be consistent over here, why don't I pick a coordinate system that I have now tilted all the way over on its side, so that as this moves in x, this moves down in x. So my x's go with my x's. Because as I go to write this, the first thing I would do is, what is the sum of all the forces in the x direction? Well, it looks like I have just one force, T1. And that would have to equal to an M1, A1. Now for completeness, I will put the y direction, but just like the last problem we did, it's probably not really relevant. I would get the normal force from this. And so there are the two forces in the vertical direction. I got the normal force up, I got mg down. I guess technically that equals m1 times the acceleration of number 1 in the y direction, but just like last time, what is the acceleration in the y direction for that one? That's a 0, which then tells me the normal force is m1g. So had there been any friction, then that would have been useful, but there's no friction in this one. Let's do friction on the next one here. But this, I guess I would say, is really the relevant piece right there. There's a relationship between tension and acceleration. If I do that over to here, I can say, well, let's look at the sum of the forces in the x direction again. And like last time, we're calling down the x direction. So this is an m2g minus a t2. And that would have to equal to an m2a2. And I'll put a box around that. And again, this one's going to take a little bit more thought than the other one by far. How many equations am I trying to find here? I mean, do I have enough equations to even solve this? What am I trying to find? I guess I'm trying to find what is T1, what is T2, what is A1, and what is A2. And what the author means by that is over here, this should be having things like M in it. You shouldn't have these other things in it. So we would like to know what is the tension based on the things given. So I don't want these other three variables. Make sense? So I've got to eliminate 3 variables. So how many equations do I need here to eliminate 3 variables? Well, let's see. If I have 2 equations and I substitute them together, doesn't that eliminate 1? And of course, then if it's 2 variables, then I can solve that. And so I need 2 equations to solve for 2 unknowns. But to eliminate 1, I got to have 2 equations. Okay, so let's see. If I had 2 equations, that would eliminate 1. So if then I had another equation, that would eliminate another 1. That's 2. So don't I need a 4th equation to eliminate 3? How many equations do I have? I got 3, right? So don't miss that. If you miss that, you're probably going to do a lot of algebra right here. Only to spend a couple hours coming up with things like 3 equals 3. Oh yeah, that's right. 3 does equal 3, doesn't it? Yeah, it means you did nothing wrong, except haven't answered the question yet. Right? We don't have enough information here. So make sure you step back and realize the bigger picture here. This is great, true. This is great, true. This is probably the hardest part of it all right here. This is great, but what am I missing? Where am I going to go from here? Now we're back to the physics again. Do you see, I don't have anything connecting T1 with T2. How can I get that? Yeah, you're seeing it. Where? Isn't this pulley connecting the strings together? So before we start doing a lot of fancy math and trying to solve this, we better do another free body diagram. But again, you got to realize you don't have enough equations. And you got to realize what you're missing before you can decide I need another free body diagram. And you got to go pick another object in here. And so here's my free body diagram. It's for P1. Now remember they said these are light pulleys. So don't worry about gravity. But what's tugging on this? Okay, obviously there's T2. Okay, what else? T1, but do you see how? Okay, so wrapped around here is a T1, but what else is happening? Wrapped around here, T1, right? In other words, the bottom part of this string, the tension on each end of it, if you will, one is on the weight itself, M1, good, that mass, and the other one is on this pulley. But as it wraps around over on the top here, there is another tension. And then somebody said the opposite is pulling on the wall here. So there is a tug on this wall, which makes sense. If this wasn't tied, you would expect it to come loose. But the whole idea of wrapping it around here is we've essentially got that string pulling on pulley number 1 twice. So again, let's pick a coordinate system. And to be consistent with our other objects, let's call it like this coordinate system here, where if it moves to the right, that's our x-axis. So as I add up my forces in the x direction, what do I get? T2 minus 2 T1, that's really the key right there, equals what? Okay, mass of pulley times the acceleration of 1, 2, 3, 4, 5. Okay, so technically I guess I would say it's number 2, but as I heard somebody else say, it doesn't really matter. I mean, if this goes down 1 meter, this comes over 1 meter. Okay, so it is acceleration number 2. But it's irrelevant because what's the mass of the pulley? 0. So they're going to give us an easy way out here in terms of mathematics. And so what they're really saying here then is T2 is equal to 2 T1. All right, maybe I should say it again. There was a lot of work here, right? You want all the answers? Can you see I did nothing more than this? 4 times. 5 really, and the vertical one didn't count for much. Okay, but I just did this again and again and again and again. That's all I did. Okay? Of course, now there's a bunch of algebra in here, so I don't know which is the best way to approach this. Maybe well, why don't I do some substitution? If I do this, this becomes T1 equals M1, and in place of A1 I can put 2A2. So that'd be kind of my first substitution. Maybe another substitution is take this T2 over to here. So this would be an M2G minus, and in place of T2 I can put a T1 equals M2A2, right? So that's what happens when I substitute that one in. And that's what happens over here when I substitute this one in. So I've now eliminated an A1 and I've also eliminated a T2. Maybe the next step is to put that one into there. So this becomes an M2G minus 2. And in place of T1, I've got a M12A2 equals M2A2. So this together is a 4. Why don't I just leave those two alone and make this negative on the other side so it's a positive. The 2 and the 2 make a 4. There's an M1 and there's an A2. The reason for that is the A2 does factor out. And so now the A2 can be solved by dividing by the m2 plus 4m1. So there's part of my problem solved. I've got the equation for A2. Assuming I've done my algebra right. There's quite a bit of algebra there. But of course, once I have that, I can get A1. So A1 then should be twice that number. So that should be 2m2g over m2 plus 4m1. So there's the other acceleration. So I've got an acceleration there. I've got an acceleration there. And as long as I have that, then I can get T1 here. T1 is A1, that number, but multiplied by an M1. So this would be 2 M1 M2G over M2 plus 4 M1. Pretty simple? No. A lot of details? All right. So remember, it's going to apply this again and again and again. Look at our patterns, solve our algebra. And to finish it up, then we can go to tension number 2. Tension number 2 is number 1, but doubled. So this becomes a 4m1 m2g over, what was all that stuff? m2 over 4m1. There we go. So I've answered the question. What is the acceleration of each block? What is the tension of each block? Ooh, well, it's taken me a little while to do those. Hopefully those were helpful. Let's try, how about 44? I said we would try one with friction. This is a good one. It does have some friction. All the ones we've been doing have been moving. So this one has some friction and this one's not moving. Okay. But let's look here and read 44 together. It says, a block of mass 3 kilograms is pushed against a wall by a force P at an angle of 52 degrees from the horizontal as shown in the figure. All right. So the figure looks something like this. Here's the wall. Here is the object. They said a block of mass 3 kilograms, okay, is then pushed against the wall. So there is a force P pushing on it at an angle of 50 degrees below the horizontal. Block of mass 3 kilograms is pushed against the wall by a force P, making an angle of 50 degrees with the horizontal as shown in the figure. The coefficient of static friction between the block and the wall is 0.25. A. Determine the possible values of the magnitude P that will allow the object to remain stationary. Well, step 1 here. Good physical picture of what's going on. Right? Got a block up against the wall. So we put it up against the wall, we're going to hold it. Is there a minimum amount of force I have to do to hold it? Well, that makes sense, right? If I don't push hard enough, what's going to happen? Yeah, it's going to fall. Okay. Fair enough. Is there a maximum force? Yeah, I push too hard, it starts sliding up the wall, right? So hence the question, what is the range of forces that are possible? It's got to be more than a minimum, but can't be up to or more than a maximum. Too much and it starts going up the wall. Too little, it starts sliding down the wall. And so, again, good physical picture. will help you with that understanding, because without that understanding, you don't completely understand the question. And when you don't completely understand the question is where things go funny and wrong. And you start making weird decisions, and you're like, well, now that I see what's happening, I don't know why I did that, but I didn't see that before. Okay? So again, that good physical picture. All right, so we got step 1, good physical picture, what's going on. Step 2, free body diagram. Free body diagram. All right, so here's the object. Ooh, do you see the forces on this one? What are they? Okay. mg for gravity, I heard that one, and I heard p for push. Good. I'm with you on that. Any others?
Friction, the normal force from the wall.
Okay, so we're touching that wall. And this is the first time today we've had some friction here. So wouldn't there actually be 2 forces here? That's what I'm trying to point out. There'd be normal force. So which way is the normal force? All right, perpendicular to the wall here. So there would be this, right? Normal. And what else? Friction. Now, a static friction or kinetic friction? Static friction, right? Remember the static friction was the inequality? Remember, static friction had to be less than or equal to coefficient of friction times normal. So that's the one that can be varied. What direction would it be? Oh, good. I heard some people say it depends on P. Why would you say that? Right. If you are pushing with a minimum amount of force, it's in danger of falling down, right? And part of the reason that's holding it up is because there's some friction between the object and the wall. And that's helping you hold it up. Now, of course, your minimum force would occur when this is at its maximum. So if you were holding it and then you got less and less force until just before it slipped, the static friction would be at its maximum and it would be upward. I only say that because what would happen if you were pushing really hard? Yeah, so really I need to think about this twice, don't I? That's why there's a range. The second option here is I would still have gravity pulling down mg. I would still have some force pushing into the wall. It would be some maximum force. There would still be some normal force. But which way would the friction be? Down. That's what's keeping the object from sliding up. And so that's why you have a range of forces there. Now again, before we can start doing any mathematics, we've got to have that good physical picture of what's going on here with our forces. Now I would claim also that at this point that it just begins to go up the wall, that the frictional force has increased and increased and increased until it got to its maximum. So even though I have this as an inequality, what happens is the minimum force means we got our maximum friction up. As we increase our force here, this gets smaller, 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 smaller. Eventually, I guess, becomes 0. Then as we push harder and harder, it becomes bigger and bigger in the other direction. Here, 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 and here until we get to our maximum. And then it's so much it can't handle it anymore and the object slides up. So that's why there is a range of force from a minimum value of P to a maximum value of P, and the friction changes direction, and that is important when we add up our equations here. So that's why I've labeled these as 2 different places here, because again, Now I can do my equations. But maybe I should pause. Did we get the first two steps? And I really think they're probably more crucial than the next couple of steps, because the next couple of steps are write out the equations and solve it. I mean, that's a bunch of math. And not to belittle the math or how complex it got, you just saw that one problem I just did. But the reality is, if you don't get this step right, it doesn't matter how good you do the math from here on out. It's not going to work out right. So you got to get that physical picture. You got to get your forces. It, by the way, is why we do the lab we do today. It's a kind of a fun lab on vectors, and give you a little vectors and let you play with vectors and let you draw arrowheads and make arrowheads and hang weights, and hopefully you'll leave the lab feeling a little bit more comfortable about all these forces involved here. Truth be told, you're going to want to feel even more comfortable, but you'll get your chance. You got 2 weeks on these 2 chapters. Then we'll move on to something else when we get into 7 and 8. But these 2 chapters are all about all these forces and adding them together. And of course they have their vectors, and so they got their components. All right, well, I need to pick a coordinate system. Anybody want to pick the coordinate system? I don't really see any advantage of switching from the traditional, unless maybe you want to call this positive sense, but I don't know. Traditional? Yeah, so let's just pick the traditional. And so we can compare the two. We'll do likewise over here for my traditional. So knowing which direction is which. And notice I just drew the coordinate system off to the side, because when we're adding vectors, it's just about direction. I don't care where the origin is. That's not relevant for this type of problem. The projectiles it was, so I tried to put the origin where the ball was being launched. But for this one, I just like to put it off to the side and say, okay, let's go to step 3. Step 3 says add up all the forces in the x direction and add up all the forces in the y direction. And then step 4 is solve those. All right, so I'm going to add them up in the x direction. Okay, what forces are in the x direction? Any x there? No. Any x there? No. Any x here? Oh yeah. Any x here? Yeah. Remember, this angle is 50 degrees. So maybe I'll start with the positive one. Doesn't this minimum force? So if I go minimum force times cosine of 50 degrees. That make sense? In fact, maybe it would be better and easier to see if I put the angle down here, 50 degrees. So there it is, and I want the horizontal component. I want the adjacent piece. I want the cosine of 50 degrees. So this is P minimum cosine of 50 degrees minus the normal force. Okay, so there's the normal force in the x direction, negative x direction. What does that have to equal? Okay, I heard a 0, which is true. Let me just say MA. But again, there's where our physics kicks in, right? You add up all the forces, it always equals MA. That's Newton's second law. That's what this chapter is about. But what's the acceleration in this case? 0. So that equals 0. And if I actually solved a little bit of the mathematics, I would have this so far. I would have my first equation that relates normal force to my pushing force. Neither one do I know. So of course, I need another equation. That's 2 unknowns, but only one equation. But I think you can see the other equation. I've got the vertical to worry about here. All right, so I'm going to add up the verticals. Well, I got a frictional force. So that's the coefficient of friction times n there. That's all upward. I've got the weight pulling down. That's mg. That's all down in the vertical direction. And the only other part in the vertical direction is part of this push. The normal one's all horizontal, so I don't have to worry about that. But isn't there a component of this one? And so that would be upward. And so it would be P minimum times sine of 50 degrees. And what does that have to equal? And that equals 0 too, right? Because it has to be mass times the acceleration in the y direction. But again, what is the acceleration in the y direction for this problem? 0. The idea is you want to push with a minimum, how much you have to do to hold it there. And so don't forget to invoke that little bit of physics there, that we can solve some of the math. We can put in the 0 there. Okay? And so, now they want us to solve for P, but I think as you can see, there's an N there, but that's where this is going to become useful. So I will put coefficient of friction times normal. Normal is how much you're pushing times cosine of 50 degrees minus mg plus P minimum times sine of 50 degrees equals 0. And of course, then the only thing I don't know is P minimum. So I'm going to do quite a bit of algebra here to save us some time. We're almost out. But if I move that over to here, then I've got P minimum in each term that I can factor out. Once I factor it out, I then have coefficient of friction times cosine of 50 degrees in that term, and then I've got plus sine of 50 degrees in that term. And so there would be my equation for what is the minimum amount of force I have to push this block. And going through the same type of problem here for what is the maximum you have to push it, well, let's add up the forces in the x direction. As you add up the forces in the x direction, I think you can kind of see this is really the same setup as that one. Nothing has really changed in the x direction. And so I've got P maximum cosine of 50 degrees, and maybe I should put 50 degrees in my diagram. Minus normal equals 0. In other words, the normal is still that same equation. Now, although it's the same equation, this is not the same value, right? Because this P maximum is more than P minimum. So there's a larger normal force here, which means there's more friction too. All right. And so there is my normal force. The one that changes between that first free body diagram we did and this one is that we've got forces in the vertical direction here. And in the vertical direction, we still got our P maximum sine of 50 degrees. That hasn't changed. We still got gravity pushing down. But what has changed is the direction of our normal force. We now have a minus mu s n. And of course, that still has to be no acceleration. So these two terms are the same, but this was a plus before because the friction was up. This is now a minus because the friction is down. But other than that sign, it's really the same algebra. So I can put in P maximum sine 50 degrees minus mg, coefficient of friction times the normal, which is P maximum cosine of 50 degrees. That still equals 0. So after I do my algebra here, I still get the mg on this side of the equation. The difference, though, is I have a minus mu s cosine of 50 degrees plus the sine of 50 degrees. So probably doesn't surprise you that you probably could have done this step real quickly once you got to here by just saying, look, this term came from the force of friction, and now it's going to be the opposite direction. So instead of having a positive sign there, I can just put a negative sign there. And if they give you the numbers, you can kind of plug it in. Well, they got a couple more little tidbits here. I think that's the hard work of it, though. What did they say here? That was find out the two equations. B says, I guess we kind of answered B. It says, describe what would happen if P was a larger value or a smaller value than these. Well, if it's larger, it goes up. If it's smaller, it goes down. And now it says put in some numbers, and they give you some numbers here, but I think you can put in the numbers too and calculate that. All right, well, we good for today? Good first step? Work on these. Some of you, maybe even most of you, it'll come straight forward, but some of you putting these vectors together and making these pictures can get a bit challenging. So hopefully today's lab will help with that. That's at least the point of today's lab.